in our campus today. So now it's my pleasure to introduce Interim Provost Kelly Klebe to introduce one of the 7. Thank you. You would take your mask. Okay.
Thank you, Chancellor. It's my pleasure to introduce the first presenter in the Distinguished Professor Lecture Series, Dr. Bob Camley from our Department of Physics and Energy Science. Bob received his bachelor's, master's, and PhD in physics from UC Irvine. He then spent 2 years as a researcher at the Max Planck Institute in Germany. In 1982, he became an assistant professor at UCCS, advancing to professor in 1991. It was in 2012 that he was promoted to distinguished professor. Bob is perhaps best known for his theoretical work explaining the giant magnetoresistance effect soon after its discovery. The discovery itself won a Nobel Prize in 2007. His research has explored nanophysics, biophysics, and the magnetic and thermal properties of materials. Bob has an outstanding research record with over 10 million in funding and about 260 journal articles, and he has won multiple campus and system awards in both teaching and research, including the Chancellor's Award in 2005 and the CU Inventor of the Year in 2012. He's mentored an incredible group of PhD students over the years and teaches courses in computational physics and nonlinear physics, to name just a few. There's a lot to say about Dr. Camley's achievements, but we want to hear from him directly. So I'll end with a few fun facts that you might not know. Bob enjoys giving talks on oddities in physics, including secret lives of dead physicists and why do scientists cheat? He also plays keyboards and guitar in the UCCS Physics Rock and Roll Band led by Jim Burkhart. So without further ado, join me in welcoming Dr. Bob Camley.
Oh, there's stuff up here I could read. This is great. You get to take off your mask while everybody else is wearing theirs. So, well, thank you for that fantastic introduction. And thank you to the Chancellor, who is still here, and to Jesse, who does everything to promote. In the first row, yes. And Jesse, who does everything in promoting research. You guys will all be officially thanked in the last slide. So now you have to stay for the whole thing. Okay, so the year is 1980. What happened in 1980? I still wasn't here at UCCS. What happened in 1980? The video game Pac-Man came out. Now, it wasn't on your PC. It was on in video arcades. What else happened in 1980? The Star Wars movie, the second Star Wars movie came out. Right? Second chronologically in our lifetime, but of course, number 5. Still going forward, Windows, the first Windows was still 5 years away. It's pretty amazing. And finally, the Apple Mac was still 4 years away. So that's what happened in 1980. And those are just to set the stage for what I really want to talk about. And what I want to talk about is this thing. In 1980, you could buy a hard disk system for $3,500 that would hold all of 10 megabytes. Now, I know that not everybody is a megabyte aficionado, so let me put it in ways that you will all be happy with. This could hold 2 songs, right? That's what, by the way, the $3,500, you notice there's an asterisk by it. Right? If you wanted to actually buy this new, because this was reconditioned, if you wanted to buy it new, it'd be $4,500. Okay. So we're now going to move to 2015, a mere 35 years later. And you can now buy a terabyte drive for only $50, not $4,500. Again, we're going to put that in terms of numbers you understand. And I understand, oh, there's what a terabyte drive looks like. You can hold it in your hand, obviously. And putting it in numbers, you can understand what will it store? It will store 200,000 songs. So that's a factor of 100,000. And even from the reconditioned price, it's 1/70th the cost, and also neglecting inflation. So this is a pretty big step forward, as you might imagine. And that's what I really want to talk about to some extent. What made this possible? What allowed this step forward to happen? And of course, the answer is it's not just one thing. It's many, many different things. But there was a major step forward nonetheless. And it was the development of a new man-made material that had properties that were fantastic compared to natural materials. And that effect was called giant magnetoresistance, and indeed it won a Nobel Prize in 2007. So this is going to be the story of my connection to that to some extent. So here is the title, how a series of my mistakes led me inevitably to explaining this Nobel Prize. And I was saved along the way, as you'll see, by many, many people. But it was amazing how one mistake after another ended up with me doing exactly that. Okay, despite the claim that you could all ask questions later, I'm happy if you ask questions now, or if you ask questions later. Get up and yell, that's fine. Any of those things are good. If you ask questions now, it'll be much more exciting because I won't know the answers. Okay, so what about the giant magnetoresistance effect? Indeed, these are the two people who won the Nobel Prize, Peter Grunberg on the right there, and Albert Fert on the left. And this was an astonishing, actually, technical and scientific discovery for its speed. The actual discovery took place in 1988. And the implementation in terms of how it was used in making hard disk memories was just 10 years later. It's an incredibly fast transition from discovery to commercial application. And you'll see this commercial application basically created more than $1 billion industry, a multi-billion-dollar industry. The Nobel Prize came just 20 years later in 2007. So that's a pretty fast step forward. And now comes the official kind of talk here. You typically put an outline in, and I didn't want to start with an outline because I was pretty sure you'd all walk out. So let me try and get the outline here. So I do want to give you, by the way, you can all relax. For those of you who are not physicists, which, I can't understand why you didn't do that. But for those of you who aren't physicists, there are no equations in this talk. There are some technical details, but I'm trying to put that at the lowest and most understandable level. So don't feel afraid here. Just relax, sit back, and enjoy your lunch. So I am going to talk a little bit about how does magnetic recording work, because I think that will help you in terms of understanding the effect of giant magnetoresistance, what role it played. I'm going to talk about GMR and how it works. I'm going to talk about how it changed magnetic recording. And then comes the part that I'm pretty sure is my wife's favorite part, all of my mistakes admitted to. And then finally, I want to talk a little bit about some stories about working with a Nobel Prize winner, because Peter Grunberg and I actually were pretty good friends. And we spent a lot of time with him and with his family. And that's probably not an experience everybody is lucky enough to have. So let's start with, how does magnetic recording work? So this is actually the inside of a hard disk drive. And what you see there is there's a disk that spins around, and it really looks, amazingly, it looks like an old-fashioned record player, right? And there's a disk that spins around, but way faster than the 33 or 45 RPM. This is 8,000 RPM, okay? And then there's a reading head that sits about 1 or 2 atoms above the spinning disk that's going at 8,000 RPM. And it is basically scanning over that thing as it moves underneath it. And that is the key, is the magnetic sensor, because that was what Grunberg and Fert basically invented, a new way of making a magnetic sensor. And that revolutionized the hard disk industry. So here's an explanation of basically how a hard disk works. Imagine, so this is that spinning disk, but it's blown up a little bit. And in that disk is effectively a bunch of little magnets. And you can see there's a North Pole and a South Pole. South Pole is, I think, red. And it's as if these little magnets are embedded in the disk. There are not physically little magnets. It's that you magnetize a region of it. Okay, so the key is if we look from the side, again, I'm pretending like there are little magnets on the top, but if you look from the side, you can basically have the north-south, and then maybe the next one is north-south. And if you draw the magnetic field lines, you will see that they look like this. The north and the south that are there, they want to attract each other, and that's what the magnetic field lines look like. Now, if you write something on your magnetic disk, it's equivalent to reversing one of these little magnets. So instead of this picture, we're going to reverse one of the magnets. This is my snazziest animation, so thank you. You reverse one of the magnets. Do you want to see it again? No. Okay, good. You reverse one of the magnets, and then you get this set of field lines, right? They're clearly different than they were before. Okay, what do you do then? You say, I need a way of reading that. So there are these two configurations, one where the field lines are pretty much contained and one where the field lines pretty much extend above the material. By the way, for all the physicists, yes, I know they now do it with vertical recording. Okay, so here are the two states. And how do you read this? You take a magnetic sensor. So you look at that little orange thing, and that's what we're going to be talking about. That was the invention or the improvement, the massive improvement by Grunberg and Fährt. That sensor, and if it goes over something where the field lines are contained, it's a 0. And if it goes over something where the field lines are extended, it's a 1. And then there's another 1, and then there are a couple of zeros. And the trick here is, what is it actually reading? It's reading something to do with the magnetic field, but what is that? And the answer is, it is reading the electrical resistivity of the sensor. So before we go on to what is the electrical resistivity and how did it change, let me talk a little bit about how this made a difference in how giant magnetoresistance made a difference in the reading of hard disk drives. So Grunberg and Fährt, they essentially developed a much better sensor, and I'll tell you exactly how much better in just a minute. And that sensor turned out to be a sandwich of iron and chromium and iron. And the key to this was that it was way more sensitive to magnetic fields. Okay, and smaller fields, meaning it was sensitive to smaller fields. And because of that, you could change the hard disk. So if you remember, our original hard disk pictorially looked like this. But now, since you're sensitive to smaller fields, you could bring up a sensor even closer and measure smaller fields. And so instead of this thing, this giant looking thing, you could shrink it down to just that little piece. And so you could store way more data on a hard disk than you ever could before. And that really was the key to making these hard disks much, much smaller, is that you could shrink everything down by making a better sensor, that one little part. Okay, so how did that sensor work? I said it worked basically on electrical resistivity, electrical resistance, and I know not all of you really are comfortable with that, so I'm going to give you some more really snazzy pictures on electrical resistance. This isn't, just to relax you, this isn't going to be as good as the previous one. So imagine you take some wire and you connect it to a battery. What's going on inside that wire? You have some electrons, and they like to move under the because of the battery. And so they move forward. Okay, great. And they move forward. Great. And they keep moving forward, and they keep moving forward. And this is the low resistance case. There's one collision. The electron hits something and is scattered into a different place. It effectively slows down for a while the other electrons move forward. So that was low resistance, right? You all know now, since I've written it up here, we're going to talk about high resistance. What's high resistance? It's when there are more collisions. It's really simple. So there's a collision right away. And then maybe you see some of the electrons move forward. That one that had a collision is scattered. It's delayed a little bit. And then it still moves forward. And then, oh, look, another collision. And I think I got one more collision out of this drawing. So that's high resistance. It's totally about the number of collisions. Okay, so that's really what you're looking at, is trying to make a material where the number of collisions is sensitive to the applied magnetic field, to the magnetic field produced by the hard disk. That's the whole key here. Okay, so now we're up to magnetoresistance. And it's basically when that electrical resistivity depends on the magnetic field. In other words, you can change the resistance, and that's what you measure. You change the resistance depending on the state of the magnetic field. And so it's called magneto, for magnetism, resistance. And now comes the really impressive thing. What is giant magnetoresistance? By the way, it's been replaced. Giant magnetoresistance has been replaced now by colossal magnetoresistance. Not replaced, but it's another effect that was even larger. So here's how large old-fashioned resistance is. Don't do that. I turned it off. In normal materials, this is about 0.5%. In other words, you put on a magnetic field and the resistance changes by 0.5%. It's not huge. In Peter Grunberg's system, which we'll study in just a minute, it was all the way up to 1.5%. And you can see that didn't sound very giant. In fact, he called it enhanced. Thus, didn't delegate, well, it relegated his paper to number 2, actually, this mistake. In Albert Fert's system, it was 25%. So suddenly it really was giant. So if you're sensitive, if you're much more sensitive, you can change the resistivity of material by 25% by putting on a little magnetic field. That's an impressive thing. Okay, so what was this invention? And the answer was, it's this sandwich. It's a magnetic sandwich. It is actually a highly technological thing. You take a film of iron, which is only 10 atoms thick, just 10 atoms thick. And then you have it's about 7 atoms of chromium, and then another 10 atoms of iron. Now, this is not easy to make. This is an important thing to understand. This could not have been done before 1980. So they were making these incredibly beautiful films of iron, chromium, iron. And it's basically a magnetic sandwich with the chromium playing the role of the peanut butter. Okay. Now, what's the magnetic state of this? What does magnetism have to do with this? Well, here's the thing that happened. If you made this sandwich of iron and chromium and iron, the 2 irons would line up their north and south pole oppositely. Like they'd be like this. You can all see it, I hope, up there pretty well. The magnetization in the 2 materials are oppositely directed. And that was a surprise. I don't think anybody really expected that, although maybe they should have. Actually, Peter Grunberg was looking for this when he invented this structure. And now here comes the key. If you bring up like a north pole, you can see there's a north pole next to a north pole, right? On the upper side, there's a north, and it doesn't like that. And what it does, here's my other really good animation. What it does is it switches the magnetization direction around. So watch this carefully. Okay. So it switches the magnetization direction around, not maybe the greatest surprise, but nice. And the key is that it changes the electrical resistivity in those 2 states. So you have basically 2 states. You have the case where they're parallel, like I've drawn here. And that turns out to be the low resistance case. And you have the case where they're anti-parallel, and that turns out to be the high resistance case. And in reality, it's not just 2 states. You can get angles between these, and you can get a whole variety of resistances. But the key is, this is why it became, this large magnetoresistance that came by these 2 states effectively is what gave that sensitivity to the whole thing. So let's talk a little bit about history. Peter Grunberg, in fact, was the person who developed this sandwich, iron, chromium, iron. And having studied it for about 8 years, he said, I know, let's see what its electrical resistance is, because we've run out of everything else to test. And he measured it, and it turned out to be that large, effectively large, larger than known materials, large magnetoresistance, 1.5%. So he was the first measurement. He was also the first patent, and that will be important. It was, as I mentioned, a 1.5% effect, and he was the second publication. And I'll tell you why in just a minute. What did Albert Fert do? He did it many times. He put a whole set of multi-layers together, and it was not 1.5%, it was 25. And it was the first publication. And the reason then why Grunberg's was not the first publication is he sent it into physical review letters. And as I've been told by a Nobel Prize winner, not Peter Grunberg, but by a different Nobel Prize winner, if you want something published in physical review letters, there, and it's basically, it's either very good, in which case they reject it, or it's very bad, in which case they publish it. That was his assessment. Despite the fact that we all send it into PRL, because it was the recognized top-notch journal at the time. And so that's what Peter Grunberg did. He sent in his 1.5% with a brand new effect going on, and they rejected his paper. Boy, do they feel stupid now. They rejected his paper. And then Albert Fert sent shortly after that something in which showed how big the effect really could be, even though the physics was essentially the same. And suddenly Peter Grunberg said, wait a minute, you just published my paper by somebody else. And they agreed to publish his paper in Rapid Communications and Physical Review B, but it meant he was number 2. Okay, so actually let's look at the history of 3 papers, the first 3 papers in GMR. This is the one by Albert Fert, which came out in 1988, November 1988. Then comes the paper by Peter Grunberg. They're both interestingly middle authors, which shows a certain amount of humility on their part. And that was, what is it? I can't read it, March 1989. And then the third paper was in fact by me and my colleague Josef Barnasch. And that came out in August of 1989. What I want to get across to you is how fast this field moved forward from initial discovery to basically some reasonable explanation, was all done within about a year. You don't get a lot of time to sit back and reflect in the world of physics. Okay, the first paper won a Nobel Prize, as you know. The second paper won a Nobel Prize, and the third paper did not win a Nobel Prize, as you know. This was entirely correct. Let me just say that. You get a Nobel Prize for discovery, and there have been Nobel Prizes predicted by theorists before the experiment, where the experimentalist still won the award and the theorist did not. So no, this was right. Okay, now we come to the best part of this talk, my mistakes. I'm not going to list every mistake I ever made in my life, but I am going to start in graduate school. 1976. I was a graduate student. I was, as most graduate students, wondering what I'm doing. I was invited. I had a solid state class from this guy, Doug Mills, who was, by the way, just an absolutely brilliant teacher and researcher. And he came up to me after the class. And he goes, you did pretty well in this class. Do you want to work on a research project? And with what you will see as my typical insight into what to do, I promptly said this word. Yes, I said no. Why? I did have a reason. To be fair, to me, I had a reason. We had qualifying exams, and only half the people ever passed the qualifying exams, and I wanted to be in that half. And I knew I needed to study, so I spent the next year studying for these qualifying exams. If you didn't pass the qualifying exams, you couldn't go on for the PhD. So I did pass, and then I went back to, I was then interviewed by a number of different groups, plasma physics and particle physics, but I actually wanted to work with this guy, Doug Mills. And so I went back to him and I said, do you have a project for me? And he said, no. No, the project I was talking to you about, I gave that away to somebody else. But luckily for me, and I really mean luckily for me, he cobbled together a project and some money to help support me. And so I ended up working for him. And 2 years later, he asked me another question. Oh, I have to tell you, I started working for him on magnetoelastic effects, which started me on magnetic excitations in thin films and magnetic behavior of thin films. And you can start to see how this connects to the Nobel Prize. So 2 years later, I'm actually about to graduate, and he asked me another question. What do you want to do after you finish, after you get your PhD? And with my usual insight and unfortunate honesty, I said, you know, I'm not that interested in, I don't know what I want to do in physics, but what I really want to do is just travel around Europe. Okay, fine. Again, nearly everybody is brighter than I am. So travel around Europe, that sounds great. My advisor said to me, how would you like to work in Europe? And so I was saved by this thing. There were 4 places in the world that were doing experiments that were related to the theoretical work I had done on magnetic thin films and light scattering from magnetic thin films. Those 4 places were all located in a small region of Europe, mostly Germany. One near Cologne, one in Stuttgart, one in Zurich and Switzerland, and one in Freiburg. Those were the 4 people who were doing these experiments at the time. That would change shortly after that. And he sent me here. It could hardly have been a better spot. And as a result, I got to know all the 4 people who were doing this work. And in fact, one of them up in the red dot at the top near Cologne was Peter Grunberg. He was doing these experiments that I was doing the theory for. And we had actually corresponded with him when I was a graduate student. I remember my thesis advisor going, he's writing out this letter to Peter Grunberg, and he basically says, you know, these German names of institutes are so long. This one is the Kernforschungsanlage, which means the Nuclear Research Center. But it was the Institute for Solid State Physics in the Kernforschungsanlage. And you had to write out the whole thing. So we had already been in contact with him. I was really impressed that he wrote back to us, actually, when I was a graduate student. And so when we met, we kind of knew something about each other. Okay, so there I am now in the right place. And speaking with a future Nobel Prize winner, I visited everybody doing those experiments. I wrote papers with a couple of them. And I was at the Max Planck Institute in Stuttgart, where I made yet another mistake. So here, if you look at the Max Planck Institute, you can see it's a gigantic building. And basically every floor was owned by a demigod. That's what the directors are in Germany. So there were 5 directors at the 5 floors, 5 directors. And I ended up working with 3 of them, which was fantastic, but it was partly a result of my mistake. So here I am, 1979, and my advisor, Peter Fulda, in one of those floors, I think it was floor number 3, says to me, what do you want to do now that you're here? And I said, I don't know. And that was fantastic for me and reasonable for him, because basically he let me do whatever I wanted, and I invented stuff that I wanted to do along the way. And so I ended up, as I said, working with basically 3 different groups. And I was doing magnetoelasticity still, which was an interest of Peter Fulda's. So he was happy with me, and the other people were too. So as I said, I worked in 3 areas: magnetoelastic effects, high spin, low spin transitions. But the one that's key to this Nobel Prize stuff, not my getting a Nobel Prize, no. The one that key was I was doing excitations in multi-layers, magnetic multi-layers. Think about iron, chromium, iron. We were actually studying that or something similar well before we got to magnetoresistance. And I was very lucky. I had, on the 5th floor, I worked with this guy, Marcos Grimsdich. So we would run up and down the stairs comparing experiment and theory in real time. It was a fantastic experience. And I was also working with Peter Grunberg in Jülich. Okay, so we had an ongoing relationship. Okay, I'm not done with my mistakes, just relax. So now I'm at UCCS and I get to do my first sabbatical, and I think, where do I want to go? I want to go to Europe. And I went to Stuttgart for 6 months. I planned to go to Jülich for 3 months. And I then went to the United Kingdom, the University of Essex for 3 months. That was my sabbatical. And it's 1988. And Peter Grunberg, he does not call me on a cell phone, just so that you're clear on this. He does not call me on a cell phone, but we do have, I basically get there and he says, you know what, we have this really exciting stuff that we discovered just 6 months ago, this enhanced magnetoresistance. Do you want to work on that? And you can see my usual sensible answer. No, and again, I still have a reason, right? I'm only there for 3 months. It's one of the shortest periods of this sabbatical. And I think I can't start and finish a project on this in 3 months. So that was my reason thing. And I was so lucky that, oh, this is a picture of the institute in Jülich, this nuclear reaction. It had a nuclear reactor and that did some solid state research as well. And they basically hid it in a forest. You have no idea that it's out there. And it's this giant facility, but they didn't want it to be too well known. Although like 50% of the people in the town of Jülich work there. Okay, I was saved from my answer of no by this guy, Josef Barnasch. He basically said, wait, before you say no, before you read this article by this guy Sondheimer first. There's the picture of the first page of the article. And luckily I didn't say no to that. I read 11 pages out of the 40 pages of this article, and I knew I could make an estimate for giant magnetoresistance. I could estimate the maximum size of it. The article, I have to give you a little hint about the article because it's back to resistivity, but the article basically reviewed work by this guy, Klaus Fuchs. And Klaus Fuchs is famous in the physics world because he was a really, really good physicist and also a really, really good spy. He worked at Los Alamos during the war. And so you might guess with the name Fuchs, he would be German, Klaus Fuchs. And he was, but he hated the Nazis. And the opposition to the Nazis in Germany before they really became very powerful was the Communist Party. And so instead of stealing secrets and sending them to the Nazis during the war, he stole secrets and sent them to the Soviet Union during the war and subsequently. He was not caught for a large number of years, actually. But he had done this really nice theoretical research in the 1930s before the war on resistivity in thin films. And so we're going to get to see these same electrons moving forward. If you have a really smooth film, they move forward without a lot of resistance. This is back to low resistance. But what if you have a rough film? What if you have a rough film? Well, then there can be collisions basically with the walls, right? With the edge, with the top and bottom of the film, I should say. And those collisions add to some resistivity. And we realized that that was using some similar ideas. That was what we could relate this magnetoresistance to. It's not that the films were rough, but we could use some of the same theoretical approaches to study the magnetoresistance. And that's what we did. So the whole point was this was related to collisions. And well, it was an interesting story for me. I made that first estimate after reading, as I said, 11 pages. The next day, Josef Barnasch comes in with a better estimate. So we're in competition, but just slightly. And the third day, I come in with a better estimate. And the fourth day, we say, this is stupid. Let's sit down. And we did. And we basically, actually it was on a whiteboard. We wrote out the outline of an entire theory for how to do it. And that entire theory working day and night, because we were really excited, as you can imagine, that entire theory working day and night took us 2 months. So we did finish it in 3 months. It took us 2 months, and the remaining month I was sick because we were all exhausted. But it was fantastic. What did that calculation that we do, that theoretical work do? Well, first of all, it explained the effect. It gave a physical mechanism for the effect. It predicted the maximum size of the effect. It explained why having more layers made the effect bigger. It explained how the effect would depend on temperature. And it did something else. Oh yeah, it did. It explained, how the resistance actually depended on the magnetic field. And so we took some data by Peter Grunberg and we did our theoretical calculation. And you can see there's two curves up there and they match reasonably well. Not perfectly. And so, there was a lot of stuff both on the theory and experimental side to do still. Okay. So how was our calculation used? Remember, it's only 9 years before it goes from discovery to production, not just production, but actually sales. And the answer was, it was used by people at IBM who built the first magnetic memories based on magnetoresistance to design their reading heads, to design their sensors, to decide how thick it should be and so on. By the way, it's not iron, chromium, iron anymore. And there have been many, many changes since then. Even by the time it got to production, it was cobalt, copper. with certain dust. I mean, there were all sorts of really clever tricks that people did to enhance this effect. But basically, the theory was used directly to make this system work. Okay, so why wasn't it discovered earlier? Why did it take so long to discover this? And the answer, as I said, was it depends on how well you can make really thin films. Right now, you can make films that look like this, where everything is perfectly in its place with 3 atoms as the inner layer and maybe 5 layers of iron, whatever you like, perfectly in place. But in those days, we couldn't do that for the most part. And what would happen is some of the iron would seep through the chromium, and it would have a direct connection between the irons and the irons. And that would prevent this anti-parallel stuff going on. So that basically meant you couldn't make this thing until the early 1980s. So you needed really good vacuum technology. Molecular beam epitaxy is what solved this problem to a large extent. Depends on atoms going in there just the right place and not having any pinholes and breakthroughs and so on. Another word for molecular beam epitaxy, you'll notice, well, another acronym is MBE, which anybody who buys or makes a molecular beam epitaxy system will tell you really stands for multi-buck evaporator, because it costs about $1 million to make one of these. We have actually in our department Zbigniew Zielinski, who made one for much less than that, and is an expert and has really done well using a system like this and many other things. Okay, just to show you that, remember that diagram I made, this is actually a picture you can take with a transmission electron microscope of you're seeing this regular lattice. That's a lattice of atoms. That's how perfect these things can make stuff. Layer by layer, perfect atomic layers. Okay, so now comes the other good part, working with a Nobel Prize winner. What is it like? I have to tell you, Peter Grunberg, who, as I said, was my friend and colleague both, was not your typical Nobel Prize winner. He was humble, he was thoughtful, he was sweet and generous as a human being. And so I wanted to tell a few stories related to that. But before we do that, before that sweet and generous as a human being, let's talk about money. Okay, the prize itself was shared by 2 people. Grunberg and Ferret, they each got about 700,000. But remember, Grunberg had the patent. And he gets, wait till you see this number, he gets 1/10 of 1 cent for every hard disk system sold. 1/10 of 1 cent. Now you might think that that doesn't sound like very much, and you would be right. But then you have to consider that there are 600 million sold in the year 2010. That's how, when you have to think about this industry, it really is a multi-billion-dollar industry. And 1/10 of 1 cent for every hard disk sold in 2010, I don't know if his patent was still operating then, but that would have been 600,000. I believe he made about 3 or 4 million personally over the life of the patent. And his university made about, his research institute made about 12 million. So not bad. Okay, now we're off the crass stuff. Peter Grunberg was an experimentalist, and he really made some major contributions to making this structure and analyzing it. And here you see him in front of the system that would have measured the magnetic resistivity. The story I want to tell you is one about being there. I was there for 3 months. Almost every single day, we had tea around 2 o'clock. The whole group, that was about 7 people. And the discussion would always be, it's iron, chromium, iron, right? Iron, 7 layers of iron, whatever, 5 layers of chromium. I don't remember the numbers. Maybe we should put another element in there, right? And so it was always, should we replace the chromium with something else? Should we replace it with vanadium? I mean, we had reasons for everything. And every single time we had this discussion, the answer would be not yet. Every time. I spent 3 months there. Chromium was never replaced by anything else. This is the life of an experimentalist. When you have something that works, you know that the likelihood of the next thing working is actually pretty small. Okay, so basically Not yet was always the answer. We had great discussions though. This is really points out the value of just meeting as a group to talk in a general way. So we would have these fantastic discussions and ideas would come out. And there was a young graduate student who, I don't want to say wasn't that bright. He was pretty good, but his real attribute was that he would listen to the discussions, figure out how to make an experiment, and a week later come back with the results. And that was just a fantastic way to move forward. So while I was there, we basically came up with a couple of different ideas that were worth ultimately writing up. And this guy basically, he'd listen to the discussion. He never contributed anything, but he would listen to the discussion, do an experiment, and out would come these fantastic results. It was really great. And, again, this is the value of having multiple people all working on one thing and having the time to work on it, of course. Okay. This is, again, a little bit of a personal history. This is Peter Grunberg's office. And the story I want to tell you is connected to the office. So I'm showing you, you see that little thing at the bottom? That's the door. That was the office. It was a big box with a door. Here's Peter's desk. Here's Josef's desk because he had been there for a couple of years. And wait, here's my desk. That was fine. Peter was, again, one of the nicest people you would ever meet. If he invited you to be there, he wanted to spend time with you. And so he would put you in his office no matter how small it was. Because what would happen? You would have these discussions. And I remember, in fact, I spent a long time at Josef's desk because there was more space there. So one time I'm sitting at Josef's desk and Peter looks up at me and he says, I'm reviewing a proposal by another group. It's this group in Vancouver at Simon Fraser University. And he is now, by the way, Peter is 6 months away past having done the work that would win him the Nobel Prize. Right? He's 6 months away and he looks and he says to me, this group is the best group working in magnetism today. And if you think about that, the amount of humility that you would have having just done something that was going to win you a Nobel Prize and saying somebody else was the best group, that's pretty impressive. The other thing, by the way, another little bit of history about that group. That group is also the group that Zbigniew-Solinsky came out of. We were connected long before we knew we were connected. The other thing that I want to tell you is when Josef and I wrote this paper, we had had many discussions with Peter and we put his name on the paper and passed it by him. And he said two things which I was really impressed with. One is he said, take my name off of it. I didn't do enough to be on this paper. It's basically a theory paper, which it was. We took his name off of it. The other thing is he gave me a bit of advice. And this is really useful advice. He said, if you want a paper to be published in PRL, because we did send it to PRL. If you want a paper to be published in PRL, you want to make sure that everybody who might referee this paper is cited in your references. That I think has been really important, and I totally would have never realized that. Okay. Peter Grunberg, as we shared an interest in guitar. I think we also played tennis together. If you came to visit him for a short time, he would just put you up in his house, basically. You would be like a member of the family. Literally, you'd have meals with them. You'd have beer in the afternoon around 3 o'clock. It didn't matter that it was a working day. I think that was the rule. Yeah. Your kids would play with his kids. It was like being a member of the family. Everybody felt comfortable there. And so that was, really special experience. And I'd show you the guitar. The last time I met with him, he died about 3 years ago. In fact, he had Parkinson's disease. The last time I met with him, he came into the institute where I was just visiting at the time, and he basically just walks in and says to me, come on, let's go. And you don't say no to a Nobel Prize winner. So I did, and he took me to where he was living, and he wanted to show me his new guitar, which had 2 necks, unlike the one in the picture here. It had two necks, and he was really proud of this guitar that had two necks. And so he gave me a chance to play it. And, we had a really nice time. Anyway, I'm going to have to read this to you. Oh, maybe not. But basically, you can probably have all read it already. But this is from Albert Ferret, his competitor. They weren't as much competitors as friendly competitors. But you can see what it says here is Peter was a sincere and humble person, and that if you spent time with him, you would talk about physics, and you would also talk about life in general and other interesting things, whatever came up. I mean, it was a full-fledged relationship that you would have with him. You could not avoid it, which was fantastic. Okay, in 1987, about a year before he did his Nobel Prize winning work, Peter was doing a tour of the United States, and he came to visit us here in UCCS and give a talk. And he stayed at our house. And this is the one picture I have of him. You can see it's a brilliant picture. This is basically, we're taking him. My wife is going to tell you that we saved his life at this moment. So we were taking him to the airport, and there was a DIA, and we basically said, I don't remember the whole story. This is so sad. We basically drove him to the shuttle to take the shuttle to the airport. And there was some serious actually injuries because it was snowing at the time. And so we might have saved his life. Anyway, this is in my garage. You can see the beautiful wallboard on the garage, and you can see him with his eyes closed, and you can see the car I used to have, which we kept for many, many years. And I always wanted to put a sign on the seat he sat in, Nobel Prize winner was here. Okay, I'm not really through with my mistakes yet, because what do you do after you work on a Nobel Prize winning effect? In my case, you almost immediately get out of the field. And I did. And I think that was actually not a mistake, as many of my others weren't mistakes, because I had some colleagues, Zbigniew Solinsky, who was also working in magnetism. And it's really tough, to be honest, it's really tough to compete with the entire universe of physicists who are now working on this effect from UCCS. And so we've actually had a lot of success here at UCCS working on things that other people are not working on. And it's also way more fun, because instead of doing something where 1,000 people are working on it, you're doing something where you are working on it. So I like that. And I just listed out some things here that I've been doing lately just for fun. This one is about making temperature visible in MRI. So you all know in MRI, you can see beautiful anatomical features. You can see inside the skull without cutting it open. And if you want to do a surgery, you might want to know one way of killing tumors is by heating them or freezing them. And you might want to know the temperature. And we developed a method of actually seeing temperature with MRI. So the light colored regions are, in this case, colder, I think. The dark colored regions are warmer. And so the brightness tells you how hot or cold the object you're looking at is. I also spent a little bit of time on something called magnetic rogue waves. I only put this in, well, because the picture is really cool. And I really like this project, even though nobody else in the world seems to. But I think Dima is going to try and do the experiment, so that's great. So there's a list here. The other thing I want to highlight is we had some work with experiment and theory, all at UCCS, and with BioFrontiers, with people in the physics department. This was just a really fun experience, because we developed a very fast switching filter that would switch from passing green light to passing red light. And what that allows you to do is to see processes that go on in the cell on about a millisecond time scale, which is like 10 times faster than the typical mechanical filters people use to do this. Okay, nothing is ever done by yourself in this world. Even if you write a paper with only you, of course, you're really dependent on all the people you've ever interacted with. And so here's a short list of all the people on just these projects. And particularly, I want to highlight that I've enjoyed working with the faculty here and the students, but I made a longer list, which still isn't complete, of many of the people I worked with over the years, faculty, postdocs, research associates. I want to say thank you to the students particularly, because I'm pretty sure I would have gone nuts without all of you. The students, if you're lucky enough to work with great students, and I have been, and I am working with them now, you really get excited. It is just a fantastic experience. But I want to do something that people don't do a lot, and I want to say thank you to the administrative people. Because I realize that, you know, you're here, or I am here at a place where we have multiple responsibilities. And the fact that we get to do research that is of our choice is partly due to all the administrative people who let us work in that environment. And so I want to say thank you to everybody on this list and not on this list. I think I'm going to stop with that because I've talked long enough. So thank you everybody for coming, and I hope you enjoyed the meal and the bit of entertainment. Okay, it's time for questions. I'm hoping somebody has a question. It doesn't have to be serious. The other option is you can tell a joke. So you're asking a question in some sense about the quantum nature. And to a large, well, first of all, magnetism is a purely quantum effect. Without quantum mechanics, there would be no magnetism. It is underlying. It is about the interactions of electrons on neighboring atoms. The stuff I actually do is not so much at the single atom level, because we typically have many, many atoms in the sensor, right? So it's not quantum at that level, but magnetism itself is quantum in nature and has to be. Any other questions? Jesse? Well, luckily I was at Jülich, and so I was connected to the entire world of giant magnetoresistance from the experimental side. And Albert Ferret, interestingly enough, aside from the making multi-layers, he had done some earlier work on the difference between spin up electrons and spin down electrons and resistivity in the previous 10 years of his life. And I read through all of that as well. And that really was giving us the hint about how to do this problem. So I was very lucky to be connected before anything came out, really. Yeah, any other questions? Yes.
Of the
yeah. Right. Right. Why doesn't it flip back? Let's go backwards to that. It's before my mistakes, though. There. Oh, if you took away that external north, it would flip back again. Right, that's the whole point. In some sense, you really have, let me say, a two-state system. If you bring up a field, it's aligned. If you take away a field, it's reversed again. And that's the whole value, because that way it says, yes, there is a field. I give you one value of resistance. No, there isn't a field. I give you another value. Oh, yes, that's a great question. That took maybe 7 or 8 years of the entire physics community wondering what the job of that inner layer was. So that that middle layer chromium is, it turns out, is an anti-ferromagnet, which in principle has layers going backward and forward from layer to layer. And it was thought that that was playing the role of allowing it to be anti-parallel. But it turned out not to be true, because it turned out you could put copper or almost any other metal in there. And it really is that it is spacing. It's doing two things. It's keeping the irons from touching, because if the irons touch, they would want to be parallel. So one thing is it's keeping them from touching, and the other thing it's doing is it's allowing electrons to transmit from one side to the other over a certain distance, and that has a natural length scale for being parallel or anti-parallel. So if you change the thickness, you could actually make it parallel. Any other questions?
We have a question from our online audience. David asks, can you elaborate further on the magnetic rogue waves?
Yes, I can. Okay. I can elaborate for a good hour and a half on them, but I think I'll try and make that shorter. So in water, let me get the picture up because that will entertain you all. In water, it is known that there are rogue waves that every once in a while basically will swamp ships, giant waves that come out of nowhere, it seems like. And we wanted to see if something similar could happen in magnetism. Could you make a magnetic giant wave? And how would you do that? And the answer was, yes, you could. And what you're seeing here is, if I can start it over again, is what you're seeing here is, almost seeing there, is letting that rogue wave decay. So we imagine we made a rogue wave, and then what would happen to it when it decayed? It would decay in this very, but it's not like throwing a stone in water. You notice it's very asymmetric and all sorts of crazy waves happen. So we were interested in letting it decay and then building it back up. So it is the magnetic analog of these giant waves that swamp ships, except on something that is a few atoms thick. Any other questions? Any other comments? Good. You just want me to stop.
You can stay right here if you'd like. But we are out of time. So please join me in a big round of applause for Dr. Camley. We are so lucky to have you as one of our distinguished professors. I do want to say thank you to everybody who, it takes a village to put on this type of event. Lindsay Copa, Event Services, Bradley Plez, our tech support today, everybody, and of course to all of you for showing up. There's more to come. We will be continuing this series, as the Chancellor mentioned, we hope every semester till we've and then we'll just keep adding maybe more distinguished professors, and we'll just never run out of these amazing talks. So semester 2022 with another presentation from one of our distinguished professors. So keep an eye out for future details for that. And again, just thank you everyone for joining. Please help yourself to some grab and go on your way out, and we'll see you next time.
By the way, since we're on this there.